next customers. Similarly, printing monthly checking account and savings account statements for bank customers is another transactional situation. The particular conditions that apply to a particular customer and their accounts determine how their statement will be printed and delivered to them, but that will not influence the subsequently printed and delivered statements for other customers. Or transactional, they're insulated one from the other. Now that is in contrast to situations like what we're going to look at with state-based testing, for example, where the sequence of events and conditions that have occurred in the past are very strong influencers of the way the system is supposed to respond. And in fact, that influence is captured in the concept of a state, which determines how those previous events and conditions affect the subsequent or the current events and conditions that prevail and occur. So once we're going to separate those things, we're going to deal with state-based testing later, subsequent webinar. We're going to deal with transactional type of situations here, the use of a decision table to test those transactional situations. Now, underneath this concept, this test design technique, is a model. It's either a table or a logical or Boolean graph that connects the conditions that exist with the actions to be taken and the actions not to be taken. Now, the thing with the model, the thing to remember about these models is, yes, there is some intellectual overhead associated with understanding the model. However, the thing about the model, what it gives you once you understand it, is that with these techniques, many of these techniques, there is a systematic process for deriving tests from the model. And what that means for decision tables and some of the other advanced techniques that we're going to look at is that it is possible to explain to someone how to use the model to derive the tests, and they will derive the same set of tests, for the most part, with some variation, as anybody else would. Now, I say with some variation because there's always the possibility that someone might apply techniques in a compound kind of way and generate additional tests, and we'll look at an example of that later. But this creates a degree of certainty about what is to be tested, and it also means that this is a concept that can be explained and mastered. Some of the more reactive test techniques, such as the use of exploratory testing, for example, is very difficult to explain to somebody what you tested and why, especially the why part. Here, with decision tables and other kinds of formal techniques, you can certainly say, these are the things that I tested, and this is why I tested them. And if you choose to transcend the technique to add additional things to it via, say, exploratory testing or the addition of multiple techniques, that's fine. You can explain that as well. In other words, it makes the testing a more deterministic type of event, and something that we can have confidence in that we know that certain things have been achieved. So back to the decision table proper. So the decision table, or a cause-effect graph, connects conditions with actions to be taken. And then there exists a process, which I'll explain to you, by which you would derive test cases from the decision table. And basically that process is going to involve making sure that you fulfill the different combinations of conditions that are shown in the table or the graph, and you check that the appropriate actions, and only the appropriate actions, were taken for any given combination of conditions. Now, along with a systematic process for the derivation of tests, there is, for many of these techniques, a rule for when the technique, the model, is done suggesting new tests to you. And these are referred to as the coverage criteria. So in decision tables, the coverage criterion is that there has to be at least one test per combination of conditions. And in the decision table, each column in the table represents a unique combination of conditions. Now, a couple of things to mention about that coverage criteria. Coverage criteria in general as a concept, and also this coverage criterion listed here in particular. Now, the word coverage is one of the most overloaded terms in software testing because it means a lot of different things. Legitimately, when I say overloaded, I'm talking about in the sense that we would use that phrase in object-oriented programming. The context determines what we're talking about. So in a recent webinar, I talked about code coverage, and there I was talking about the structural coverage of the system. How many of the statements, what percentage of the statements have been executed, what percentage of the branches have been taken, and so forth. And so code coverage is one kind of coverage. Talk about requirements coverage. Is there at least one test for every requirement specification element? Risk coverage. Is there at least one test for every risk item that's been identified? Design coverage, looking at design element coverage, supported configuration coverage, workflow coverage, use case coverage. There are many different ways of looking at coverage. But we don't mean those ways that I just mentioned here with these techniques. Coverage here refers to coverage of the model. In other words, every element of the model that suggests a test has been addressed. That doesn't mean there aren't any more interesting tests to create. Of course, there are, and of course, with most real-world systems, there are an infinite number of tests we could create. Achieving the coverage criteria here means is the particular technique, and in this case we're talking about decision tables, done suggesting new tests to us. Now, to this coverage criterion in particular, I notice it says at least one test per combination of conditions. So that suggests a certain flexibility in that there might be more than one test. And of course there could be, because there could be multiple interesting ways in which a condition could be satisfied or not satisfied. And conditions might be defined on ranges of values that have minimum and maximum values as well. So this opens up the possibility of applying equivalence partitioning and boundary value analysis to those conditions, which I will demonstrate a little later in this presentation. Now, with all of these techniques, all the advanced software testing techniques that we're going to talk about in this series, which, as I said, will go on for as long as we all find it interesting and useful, there is an underlying bug hypothesis. This is a term from Boris Weiser, back to software test techniques at least. The bug hypothesis is, what kind of bug are you looking for with this technique? Which is, of course, also a good way of deciding, should I use the technique, yes or no, because if the bug hypothesis is not of interest to you, you don't care, then you don't really have any interest in using the technique. So it's always good to ask yourself, well, what kind of bug is this technique good at going after, and is that what I'm trying to do here? Is that related to the objective of the testing that's underway right now? So for decision tables, the bug hypothesis is that there will be, under some set of conditions, an improper action taken, either the completely wrong action, the one which was supposed to not be taken, is taken, or the right action is taken, but it's carried out in the wrong way. It's carried out improperly. Or, alternatively, the possibility is that there's an action that is supposed to be taken and it is not taken at all. Some important bit of processing that the application was supposed to do doesn't happen. So those are the kinds of things that we're looking for, and as you can see, those are related to the business logic, doing the right thing based on the particular situation that the program finds itself in. Okay, so let's look at a decision table in particular. Now, what we're going to use here throughout this